Good afternoon and welcome to the first session of the first edition of Instituto Superior Técnico's MasterTalks. So every month until June, we'll have a Master Talk dedicated to each of the Instituto Superior Técnico's departments, in which we'll invite a professor to share some of their research, followed by a moment where you can get to know each of the department's courses in detail outside at the atrium. At the end of the talk, there will be time for questions, okay? You can ask your questions here, live, or you can ask them via the QR code you see on the screen. And today's session is dedicated to the Mechanical Engineering Department. It's a pleasure to have with us Professor Paulo Ferrão, professor in the department and a researcher at the Center for Innovation, Technology and Policy Research, to whom we'd like to thank in advance for accepting our invitation. In our desire to achieve a more sustainable world, it's imperative that we explore the mass and economic flows for our societies. So I give the floor to Professor Paulo Ferrão, who will show us how mechanical engineering promotes efficiency to achieve this goal.
Thank you very much. So it is really a pleasure and an honor to be with you today to discuss a few items, a few questions that I believe are relevant today. And I believe that we share one common goal, is that we want to be more sustainable than we are. So, and the question is, if we aim for sustainability, we need to better understand the world. The world as in effect, as a metabolism in a certain way, as a machine in another way. So certainly we need engineering to understand the world. And today I need to say that we need to have mechanical engineering to understand the world. And then I will try to provide you a travel through some main questions of sustainability, and then how mechanical engineering addresses it. Of course, combining with some research that I do and other research that is done in our department. Now, some data to start. We certainly have a problem, is that we consume too much. And I would like to share with you some data, which is resource extraction, and we call resource extraction to whatever resources we extract from Earth, so whatever we dig from Earth, has more than tripled since 1970. And I think this is very impressive. And it includes a five-fold increase in the use of non-metallic minerals and 45% increase in fossil fuel use. And what is even more troubling is that by 2060, global material use could double to 190 billion tons from 92, while greenhouse gas emissions could increase by 43%. So this is to set the stage. Of course, the numbers I provided to you are flows. And that's why I would say that environmental and economic sustainability are about flows. So we need to understand the flows across the economy, the flows across our society, the flows of materials, the flows of money, in order to better understand how can we be more sustainable, each one of us all together. And of course, this is mechanical engineering. So that's my motto today. Now, let's go into some science behind it. So the first elements that we teach here in mechanical engineering is to understand material flow analysis. So material flow analysis in terms of the economy work like this. So first of all, we consider the economy, and the product or a material goes into the economy when we pay something for it. So for example, if I take a potato from the soil, we are extracting. So this is a domestic extraction, if I extract it in Portugal. And as I pay for it, I count it as something that entered in the economy, okay? For example, if I import a car from the outside, so this is an import, this is not extract domestically, and the domestical space is this green one. So we have imports and domestic extraction. So the sum of the materials that we use in our economy are the imports and the domestic extraction, which is called the direct material input. So this is the material that enters in the economy. And then what do we do to these materials? Well, for example, if we make a building, given a certain year, the building stays as a stock. But others, if we eat the potato, for sure we dump it as waste a little bit after. So most of our materials will be discarded as environmental problems in a certain way. So these are domestic outputs. Where can the domestic outputs go? To the soil, to the water, or to the air. So, and that is, of course, a main problem in environmental sustainability. So you cannot understand how to reduce pollution if you do not understand how the materials enter and circulate through the economy. I think this is very obvious. And then, of course, we have a little bit of exports. Now, I'm sure that all of you have already heard about something which is very popular now, which is circular economy. So, and my question is, do we have a circular economy, for example, in Portugal? And the response is here. So this is data from Eurostat. I want to tell you a few numbers that are for you to remember. So this is the amount of materials that we extract per capita per year. So each one of us, of you and me, we eat 14 plus 6, about 20 tons of materials per year. So due to our lifestyle, each one of us eats 20 tons of materials. I don't know if you had this idea. So it's not only what you eat at the table, but of course, as you use transportation, you consume fuel. As you are at IST, construction materials were used. As you use a car or a bicycle, the materials that were necessary. As you go to a football stadium, so there is also a lot of materials that goes into the football stadium. So each of us consume 20 tons of materials per year. Out of these 20 tons, so part of them, 12, are accumulated in our economy. And then we have a lot of emissions to air. We have some exports. And look, this is how much we recycle, 2%. So is our economy circular? No. So it's a fully linear economy, which is terrible. So we extract raw materials, we transform them into pollution. And of course, this is a problem. So the question is, does it have to be like this? Well, let's go back to the research I did some years ago. This was by 2003, and I guess we were the first, in a certain way, to demonstrate that the GDP, so the money that the country generates, when the economy is developing, say, for example, China in the old times, or India, or whatever. So if we have a GDP of about 2,000 euros per capita, we would consume about 3 tons per capita. And then we start to get a little bit more rich, but guess what? The consumption of materials increases almost proportionally. And this is very dangerous for sustainable development. It means that the nations, as they start to get richer, they consume more, they produce more, and they dump more in the environment. Is that clear? And this is a problem. When the economies start to get richer, about 15, 20,000, it seems that it tends to, tends to equilibrate, but there is no evidence that this can go down. I will show another thing from some results, but of course this is a major concern. So resource productivity, resource productivity is the amount of euros that you can take in the economy from taking 1 kilogram of material. So here, resource productivity, when this is at 45 degrees, it's constant, so it's not increasing. You produce more, you consume more. Here it starts to increase, but only at a very high level, okay? And at very high consumption rates. This is one of the most fundamental problems of sustainability in the world. It comes out of this. So, and that will be the motivation for many different things. Well, after 18 years, we have been thinking with students from mechanical engineering how to solve this problem, how to understand better the metabolism of the economy. And the metabolism of the economy is, what I have shown you is that we eat 20 tons, something goes out and it produces some money. But where did it go? How can I improve it? So then we need to much better understand the flow of the materials through economic sectors. This is the metabolism in the sense that we can look at the different economic sectors, if they are different organs of the human body. So these are the organs of the economy in a certain way. Of course, it's not my purpose today to explain this very much in detail, but what is very nice is that we need to marry engineering with economics to do this. And this is something we do in mechanical engineering. So what we do is we combine inter-industry tables, the famous input-output tables from the economy, which are provided by the National Institute of Statistics, with materials froze extracted. I will not bother you this. Come to mechanical engineering. You can study this in more detail. And then what we did is we organized different classes of materials, 17 classes of materials, and we developed this new model. And this was the PhD of a bright student, a lady by the Sonia last year. The problem is, of course, she was already kidnapped by the Dutch, so she's now working in the Netherlands, which is, of course, good for her, not so good for us, I guess. And we can do this for any country in the world. And this is the type of result that we get to understand the dynamic of flows, and we can explain, for example, crises and the metabolism of the economy. I will show something that I find very funny and very easy to understand. This is the result of the work. For example, this is Portugal. So Portugal between 1996 and 2008 has increased the GDP from about 14,000 to 18,000. And guess what? It was a steady increase in GDP accompanied by a steady increase in material consumption, which again, more pollution, more whatever. Okay? Now, it came the crisis. As I used to say, no money, no vices. So what happened with the crisis? So we had less money. Guess what? We consumed. This is from 2008 to 2013. This went to the left and came down. Some of people could argue, I'm not arguing that, oh, that's fantastic. If we get poorer, we get more sustainable. We know that by COVID, we know that by, is this what we desire? No. So then Portugal started again to grow economically, but that's very good news. We didn't recover the same pathway. So we really became more sustainable. We increased GDP with much less, you see, material consumption. Now we need to understand why. Why is this? And then we need the method that we have developed. The next slide shows you that the productivity of the different economic sectors is very different. Productivity of a sector, what is it? How many euros you generate per kilogram that you extract from nature. And then, for example, you see agriculture, unfortunately, is very low. Mining is horrible. So it's close to zero. So you need to consume a lot of materials and then you get very, look, GDP is the value added. So, but you see many sectors like textiles, wood, paper, plastics, electronics, transport in a certain way, services produce much more money per unit of material consumed. And really, what happened in our economy is that we came out of a construction-based economy to a more service-based and to this type of sectors. And then this explains this a little bit. Now, I would like to invite you to go into a travel of trying to understand what happens to materials in our economy. This is the diagram that we have developed to explain the metabolism of the economy. And here you see these are materials. So for example, this is domestic extraction. This is imports of materials. And now we are going to see where do these materials go. These are economic sectors. And then just bear with me. So domestic extraction, materials are flowing into the mining sector, not surprisingly. So it is the minor sector that extracts the material from the soil. And then the mining sector sells, for example, sand to the construction industry. It also sells other products, for example, to make tiles or something like that in the other sectors. And then, of course, the tiles are sold to the construction industry. And then construction is selling this to gross fixed capital formation, which is basically the buildings, so the stock. But also, you see, a lot for services. So we cannot say that services are not materialized. Services consume a lot of materials as well, not as many as others, but they consume a lot of materials. And then, of course, there is also an interaction between gross fixed capital formation and services. So this is important for us to understand policy. So, for example, a few years ago, the Minister for Environment asked us, well, is it a good business to invest in kaolin extraction? And the response from this is absolutely not. It creates a lot of environmental problems. It doesn't provide jobs. It doesn't provide any added value. So this is not so relevant. So this is the type of thing which is relevant. So this is science. This is research. And then you can ask, but why do we do this? Many reasons. Now I give you examples of what we in mechanical engineering are contributing to the country based on this type of research. For example, before 2020, we were the coordinators of the National Waste Management Strategy and also Persu 2020, which is the National Action Plan for Waste Management. And why was that? Because along the years, we have developed the capacity to model the processes that are required to recycle whatever. So to recycle a car, for example. For example, it was also in this department where we created the companies that now are responsible for recycling, for example, cars, which is Valor Car, tires, Valor Pneu, electric and electronic products. Why? Because we had the capacity to model the recycling processes and to calculate how much would it cost to recycle a car or a product, which are the best pathways, and of course this is in the root of this. And this is of course because we have laboratories, so together with the mining industry, laboratories where we are really testing recycling technology. So this also happens in mechanical engineering. And for example, now we are very occupied with a central problem, which is, for example, to recycle what? Batteries from electric vehicles. This would be critical, otherwise we are doomed. So if we do the electric vehicles, a lot of materials consumed in the batteries, maybe 1 ton of batteries per car, something like that. And we don't know how to recycle, we have a problem. Yes, so we are also working on this. And what I want to call your attention is to these practical things. This is mechanical engineering. Now, if we aim for sustainability, you would be expecting, I guess, that I start to speak about energy. And now I will. So let's turn our attention into energy. And the question is, we want to be climate neutral. You know what means climate neutral? So we want basically not to emit CO2. Or if we emit, we need to capture it. And this is very, very, very complicated. And of course, we are here to provide some guidance on how to do this, on why and how. Again, I would like to draw your attention to something that we already discussed, is that we are in this situation because we are consuming like crazy. So this is the use of primary energy in the world. You see, 100 years ago, 50 years ago, 70, and then boom. So energy consumption in the world increased like crazy. How much is crazy? Crazy is this crazy number that I don't want you to remember, but just for 10 seconds maybe, or 30. So the total consumption in the world, the supply consumption is 163,639 terawatt hour per year. Well, this is a number. This is this number, the total that we consume. And now we have the ambition to make the world based on renewables, don't we? So we want all this energy to be provided by renewable. By the way, let me interact with you a little bit. Where does renewable energy come from? Can you give me examples?
Solar energy.
Solar energy. And basically that's it. Because we have solar energy, wind energy. Where does it come from? The sun. Because there are different in temperature, different in pressures, and then it generates the wind. The wind generates the waves. Well, basically it's all solar. So it's not solar, for example, a very tiny, which is the tidal energy, for example, and this comes from the moon. The sun and the moon, but of course the moon is a very little energy source. And then of course we have from the interior of the earth, geothermal energy. Okay? But basically everything comes from the sun. So I have another challenge for you, another question. Do we have enough solar energy to supply all this energy? So is it really a good bet to say, oh, let's invest in renewable energies? Well, let's make some calculations, very easy calculations. So this is the number we need to supply. But how much energy comes from the sun? This is a number you can keep in your head. So the solar energy that reaches the atmosphere is about 1.4 kilowatt per square meter. So when you go into the sun, into the beach, it depends on the latitude, of course. This is if you are just perpendicular. It will be maximum 1.4 kilowatt per square meter. Well, this is the total solar irradiance. And then you can make a very simple calculation. If you know this, and then you know the diameter of Earth, you can say how much solar energy eats Earth. Okay? So that's a very simple calculation. And then if we have this consumption of energy per year, and then if we divide this by 365 days and 24 hours, so we have a power consumption, average power consumption of about 18.6 terawatts. So this is the energy consumption that we have. I would like to drop you another number. If we divide this by the population of Earth, this means that each of us, in average, and the average is much less than in Portugal, in average, is consuming 2.4 kilowatt. So we, to keep our society, generally we have a 2.4 kilowatt consumption in the world, each one of us, at each second of our life. Now, if the solar power reaching Earth's atmosphere is 173,000 terawatt, well, this is good news, because this is how much arrives to Earth, this is how much we need. So there is this striking number that the sun provides us almost 10,000 times more energy than what we consume. Good news. Good news. 10,000 more. So this would mean that in a Star Wars language, dream we can, but mechanical engineering we must. A little bit of electric and others, I guess, but okay. I will speak a little bit about that, because mechanical engineering is also about control, is also about electronics, is also about these things. Of course, I have the president of the electric and electronic, but okay, he's my friend, so. Now, it's not as easy. I had in the past, so this would mean, let me go back and forth a little bit, that if we put solar panels in a very, very tiny fraction of Portugal, we will have the energy problem solved. Maybe. But the problem now is this becomes a different paradigm. I'm sure you have heard about this different paradigm. So in the past, we produced electricity. These guys, the electrical engineering, were very comfortable. They dispatched the electricity. We consume it. Not anymore. So if we are using the energy from the sun to transform it in electricity, each one of us in our homes produces electricity. So the electric grid is no more in one sense. It comes everywhere. And also, this is the energy consumption in one day in Portugal. So energy consumption varies a long time. And this is how it is supplied. For example, here it is natural gas. Here we have solar, for example. This is hydro. This is coal. So it varies with time a lot. So we have one problem with solar energy. What is it? Unfortunately, the sun is not there during the night. So if we will fill all the energy requirements, and the energy is the area of this diagram, we need to have, and this is the typical diagram of energy supplied by the sun, we need to have a lot of solar panels, yes, but we need to store a lot of the energy produced during the day to feed in the night. How do we store? How do we manage this? So the equation now is about time and space, because it depends on the space, on the place where the energy is produced and consumed, the electricity, and the time it's produced and consumed. So good news for us engineers, good news for you, a lot of jobs. Because this is complicated, very complicated, and we need a lot of brain. So it's no more a stupid system. You need a lot of intelligence to do this. And I had, so for example, we in mechanical engineering have produced this last year, which is energy storage in Portugal. And of course, we have come to the conclusion that our pumping storage capacity in Portugal is not enough to store all that. So we really need to be doing better and brighter. I am 6 minutes away from the end of this talk. So this is politics, goes very fast, it's done. This is just to say that we have very ambitious targets for renewable energies. They are there, so the jobs are there, because needs to be accomplished. This is a revolution in the making. Let me give you another important name. From year From year to 2030, electricity consumption will double. This is good news for these gentlemen as well. Will double. So we need to invest a lot in solar energy, in wind energy. And guess what? This is mechanical engineering. So my colleagues which are there, and I am from, I will need to say, from mechanical engineering has different sections. I'm from the sections of energy environment, not surprisingly. And my colleagues that I try to represent here, they have a lot of work to do as well. So you can go to their areas. This is all mechanical engineering, and this is all going to solve the problems in the world. So which problems? We need to better model the ocean. We need to better model the rivers if we want to design the wave energy systems, the hydraulics, the wind turbines. We need to understand the wind. So all of this is provided in mechanical engineering. For example, here at IST, we have prototypes of equipments that produce electricity out of wave energy. This is the lab of production mechanical technology. We need to manufacture all this. This doesn't come like that. So you need this. And then we have a lot of structural and dynamic assessment. For example, when you put one turbine in the ocean with the tripod, you need to very much understand the structure. It's very important that it's light. It's very important that the dynamics are correct. So all of this is mechanical engineering. So I have a challenge for you. Not done before. Do it now. There are a lot of interesting groups in mechanical engineering, like the FST, MOTO, and so on. Why don't we take this in our hands and make of IST a better IST, made by you, the students? So my challenge to you today, let's create a student team on energy management of IST. I was already the responsible for energy management at IST with my colleague Mario here. And if I don't take a tomato or a green thing, this is a lady from Galp that supported us by the time. So, and guess what? We got the prize in the United States in the World Energy Conference of the best project of the year by then. And this was to make the IST more energy efficient. But this is not enough, and we cannot do more. We, the faculty, we cannot do more. I ask you to join. So as you see, as a result of our project now, you have seen these maybe. These are solar panels that are now being incorporated in all the roofs of IST. But now we need to manage these with intelligence. A lot of thesis for you to make, a lot of work that needs to be done. And I would suggest that you create also a group to manage energy and sustainability IST. This is very important, and it needs to come from you. Managing this is automation and control, and this is mechanical engineering as well. So you need to control the dynamics, to switch on, to switch off. This is what we call demand-side response. So we need to manage if there is sun now, and then all of a sudden there is no sun, I need to switch off some equipment eventually. Otherwise, I need storage that is very expensive. So we need to be very smart to save money. Smart is your business. So don't forget about this. But we need to have much finer models. My last thing is to present to you a model. So there is now a mission in the climate in the European Commission, which is to promote climate neutral cities in 2030. Climate neutral cities. So a city that does not produce net CO2. I'm very proud to be one of the 15 persons that is working in the Commission to develop this and following this apart. And of course, this is part of the work that we do here. And what we do in our labs, and of course I would also invite you to do this, is to model cities. To model cities, because of course it's very important. Cities are home of 75% of the European citizens, and they consume 65% of the energy. So let's see how we model energy, how we model the city. Now we are making computer models of all the cities, of all the buildings. How do we do this? We characterize, for example, Lisbon buildings in different types of buildings, for example, in the Pombal buildings or the buildings here near us, so they have different construction materials. We model each building, and then we know that the buildings are placed in the soil in a certain way, and then the computer goes and reproduces the buildings with their building characteristics, window to wall ratios, And this is just a demonstration of how we are doing this. This is, for example, a zone of Arroios, so near IST. And then the computer now will recreate the buildings, making a box so we know how tall the building is. And here the advantage and what we do in a unique way is to model not one building, but all of them. So this is the model of the buildings. The colors would represent, for example, different energy intensity in the buildings. And then I can simulate, because the physics of the building is there, and I know if the building is on the shadow at a certain time, I can simulate energy consumption for heating, cooling, and lighting at any hour of the day during the year. And I can, for example, simulate how much do I save if I increase the insulation of the building, if I change the window, if I change, for example, the lights, or, of course, if I put PV generation. So this is mechanical engineering. This is something that you can do with us. So, and of course, this is relevant and this is important. So, come and contribute to something that we are developing in a unique way worldwide, which is to build what is now called the city's digital twin. So this is a city digital twin. We are now adding the mobility component. And my last slide, why is this important? Well, this is important because of you, because you matter in mechanical engineering. I hope this was a journey through what you can do in mechanical engineering, and I hope you understood why engineering, and in particular mechanical engineering, is important for sustainability. Thank you for your attention. Thank you very much.
So I would like to thank Professor Paulo Ferrão for this excellent presentation. I myself thought it was very informative. I invite you to move on to the atrium after our question session, let's say, where you can talk to the professors from each master's degree. And to talk with some of our members from technical support services, can give you some answers about technical support, resources and initiatives as well. So I would like to give you now the stage to ask any questions that you might have. And does anyone have any questions? You can rise and ask your question. I'll repeat it so it's recorded.
Questions, comments, come on, show that you are alive.
Please.
Ah.
Thank you very much for this really informative and excellent presentation. I would just like to ask you something. You talked a lot about mechanical engineering. So how does this relate with the other degrees that we have in mechanical engineering, like environmental engineering, materials engineering, aerospace engineering, naval engineering?
Thank you.
So the question is, how does this relate with material engineering, mechanical engineering, naval engineering?
Yeah. Well, in fact, in these courses that we are providing, in fact, we are providing these courses to all of this type of engineering. So the relation is very, I think, very obvious when you speak about environmental engineering. So as you may know, environmental engineering is the only degree, I guess, that does not have a department. So it is run by 3 departments. So mechanical engineering, civil and chemical, isn't it? Correct? Mais 2? Which are they?
Bioengineering and energy resources.
Bioengineering and energy resources in mining. This is very critical. I need to say all these things correct. And of course, these are cross-cutting. And by this way, in fact, the different courses are very much related. So we have here a colleague from aeronautical engineering. I'm sure aerospace engineering. I'm sure he had a lot of this type of materials, and we'll have more. And let's say at the end of the day, this is all engineering. So you are in the right side of the moon, I would say, of the sun. I don't know. But we all together need to cross-cut barriers. I would like to say something which I think is important. In the past, people were very much siloed. The secret of the future is really to cross-cut between disciplines. So as I think I try to show you, for example, I try to cross-cut between economics and machine and energy and thermodynamics and electronics, and you will need this. This is the difference from an engineer in the past and an engineer for the future, okay? So the capacity to cross-cut, because the problems are complex and we cannot get siloed.
Are there any more questions here? I do have one question. So how can we as students contribute for a more sustainable world, and how can we locally at IST contribute as well?
Thank you for that question. In two ways. So the first way, which I am a very big fan, is to organize yourself in groups, and I think we really need more of you organizing yourself to solve problems. I left here a challenge to you, so let's organize a student team, for example, to make Técnico carbon neutral. This will be an awesome thing. And another thing is that you need to understand is, so the Department of Mechanical Engineering or any other department then has different research centers. And the research centers are eager to welcome you, to work with them in projects that make a difference. For example, I try to show you some examples of projects which are real projects that we implemented in Portugal, from policy making, from working with companies. And I would also invite you to come to these research centers. So, for example, there are different centers of mechanical engineering presented here in this room. And offer yourself to work with this research center in very interesting projects from moment one when you start the master. I think this is very important. And eventually, there are still some grants that will eventually support you and have you then doing research that then will be applied. As you know now, there are a lot of opportunities with this PRR, and try to get engaged. I think this is one of the major strengths of IST. IST is involved in many different projects on technological development, societal development, policy making. So don't be shy. Go into the centers, speak with the people, speak with the researchers, and start to engage in research from the first moment. So this is, I think, a piece of advice that I would like to leave with you.
Sounds good. Does anyone have any more questions here? In the meantime, you can always submit your questions if you're a little shy, let's say. So please feel free to submit your questions here with the QR code. If not, I have a few more questions for you, if I may. So, given that Portugal has a huge coastline, thank you. Are there opportunities for us to do master thesis on this topic? And is there any current work being developed at IST on this matter?
Yeah. Are you a surfer now?
I would like to become one.
Well, that's one project. So on the coast and the sea. But apart from surf, so of course, so there are many different projects you can work at IST on the sea. So for example, there is a lot of work now, particularly in research work on offshore wind, for example. This is one. On wave energy, of course, this is another one. And you see, that's a good example. If you look at this, you have so many different science behind it. So as I tried to show, and now I have opportunity to develop a little bit, you need to understand better the resource, the wind or the wave. And then if you like mathematics, great opportunity. So these are mathematical models. IST is a pioneer worldwide, for example, in a mathematical model, which is Mohit from our colleague Ramiro Neves, which is used all over the world. Just to model the sea, the waves, and even the estuaries and all this interaction. And then, of course, you can work on that if you like mathematics. If you do not like so much mathematics and you like mechanical production or construction, so the sea has very harsh conditions. So you need to really advance on the welding, on the manufacturing, on the design of machines so that they can withstand the conditions of the sea. And that, of course, is very, very critical, very difficult. You need to do lightweight. And then and then there is also colleagues here that work, for example, a lot in dynamics. So the dynamics of the machines are very, very important because you see they have the waves, they have the wind, they are rotating. So how can you equilibrate these? And again, naval engineering. So this is more a little bit on the naval engineering. And then above all, you have control and automation. So all of these can only be done in very, very fine work on control and automation because of what I have said. You need to model and to manage in time and in space. So you need to make sure that you can, as much as you can, promote what we call demand-side response. Say, for example, if you have a home and you have some solar panels, so during the day, you will have much more energy than what you need. So eventually, if you have an electric car, you can give an automatic action for the electric car to start charging. But then there is a cloud. The system would need to disconnect this, for example, you see. And all of this requires a lot of integration of things that you can do all over, all over the spectrum of the mechanical engineering areas. Yeah.
All right. Yes, please.
What are your thoughts about nuclear energy?
Yeah. Let me say, this is a philosophical question. Let me transform this question in another one. How long is the idea of future for you? If you say the future is in 10 years for you, 50 years, or 100 years. So let's vote. Your concerns are 10 years away, 50 years away, or 100 years away. Who is 10?
10 for sure.
10.
Can we vote more than one?
No. 10 years. Yeah. Okay. What did I say?
50 or
50. 50 years. Okay. 100 years. Okay. So, and if you go into environmental science, I would like to invite you to speak with my colleague, Professor Tiago Domingos. I guess he is much better than I am on this. So this has philosophical implications, of course. And why I'm asking you to respond to this question? From a pure resource matter, I would say if you are worried with 10 years or 50 years, nuclear is okay. Because there are resources that can provide energy during that period, apart from the questions of the risk or whatever. If you are worried with much more, it might not be such a good option. Now, what is the problem of nuclear? For example, it depends. I told you that energy is to be managed in space and time. So, for example, in Portugal, again, I was very much educated by a professor here at IST, Professor Delgado Domingos, and he was very much against nuclear. And I think the main reason I learned from him is very simple to explain. The problem of nuclear is that it is on a very big scale. For example, if you would have a nuclear power plant in Portugal, well, you would not need more renewable energies or whatever. And of course, this will be very bad because then you have a monoculture in a certain way. So, and this is why I think nuclear is not so good. Now, the future of nuclear, in my opinion, is what it's called small modular reactors. So much smaller reactors, which then can be combined with other energy sources. And in my opinion, this is good. So you see, it's not such an easy answer. So smaller scale nuclear, it might be good for providing solutions in the short run, short medium. So the 50 years of what we have spoken. And then, but they should not preclude the use of renewable energies, which of course are much more sustainable. Okay? Was this clear? Oh, yes. Yeah.
All right. Thank you, everyone. I'll leave you to visit all our departments or the representatives of each department at our atrium, not without telling you about the next session. Right, so next session is on the 19th of October. This session is dedicated to the Department of Electrical and Computer Engineering with the Professor Mario Figueiredo. And you can sign up now, all right, at Eventbrite. And I'll leave you now to visit our stands and talk with everyone there. I hope you enjoyed it, and thank you, everyone.
Thank you.